Hello everyone and welcome to lecture. Today's lecture will be about the partial derivative and various other aspects and ideas related to the derivative of a multivariable function. Specifically, we'll talk about the differentiability and what defines a differentiable multivariable function. So we'll start the lecture by defining the partial derivative. And luckily enough, if you recall from Calculus 1, the definition of the single variable derivative, you'll be very, very happy to know that the partial derivative extends directly from that idea. So if you remember back in 1D, the derivative of a function, also sometimes called the rate of change of a function at a point, is essentially the slope of the tangent line at that point. So let's say this is our function. Looks like this may be the derivative at any point x naught, or we'll say this is the x-axis, this is the y-axis, and this is the curve y equals f of x. The exact mathematical definition of the derivative is that it's the limit as delta x goes to 0 of f of x plus delta x minus f of x naught. Oh, this needs to be x naught divided by delta x. And this is very, very commonly said to be f prime of x naught. Another possible notation for this that's very common is dy dx at the point x naught, to indicate that this is being evaluated at the point x naught. So you'll remember that this idea essentially gives us the slope of, it's said to be the tangent line of the function at a given point. So the slope of that tangent line, or the linear approximation of a function at a point, is exactly this limit. The reason being that if you look at this difference quotient that you're looking at right here, this difference quotient for any delta x, say between x naught here and x naught plus delta x, this difference quotient is the slope of what's called the secant line, or this line right here, the line between this point and this point. And as delta x gets smaller and smaller and smaller, this secant line approaches the tangent line to the function at a point. So if the function is differentiable at a point, then we say that this limit exists, and the function is best approximated by this tangent line local to the function, or around the point x naught. So local to the point x naught. We can almost directly extend this idea to define the partial derivative of a multivariable function. And in this lecture, I'm just going to consider a multivariable function of two variables. But hopefully you can clearly see, once you watch the lecture, that this extends to a function of any number of variables. We can actually extend this idea to functions of 3 variables, 4 variables, really any number of variables that you want to consider. So we define the x partial derivative of a function f as follows. And the notation is a little bit, it's similar to single variable calculus, but the notation is also a little bit different. So we actually introduce a new symbol called the partial derivative symbol to denote the partial derivative of a function with respect to x being evaluated at some point. This is now a point in 2 dimensions for a function of 2 variables, r0, where r0 is just the vector x0, y0, just some point in 2D space. So we say that this is equal to the limit as delta x goes to 0 of f of x0 plus delta x, comma y0, minus f of x0, comma y0, divided by delta x So it's very, very similar to how we define the single variable derivative for a single variable function. Is that the partial derivative is the single variable derivative in the direction of the coordinate x. What that means is that we also have, for a function of 2 variables, we have 2 partial derivatives. We have a partial derivative in the direction of x, and we have a partial derivative in the direction of y. And we say that if both of these limits exist, then we have existence of both partial derivatives. Or if only one of these limits exists, then we only have that one of the possible partial derivatives of the function exists. But you can see that for a function of 2 variables, we have 2 separate partial derivatives that in general give separate values. For a function of 3 variables, then you'll have 3 partial derivatives, an x partial derivative, a y partial derivative, and a z partial derivative, and so on and so forth for really any number of variables. For a function of 5 variables, you'll have 5 partial derivatives that correspond to the each individual component of that function. The key takeaway here for us is that really the definition of these partial derivatives is based on the limit definition of the single variable function. And because of that, right, when we go and calculate, say, the x partial derivative, we can use all of our derivative laws from single variable calculus. So the product rule, the chain rule, the quotient rule, all of the derivative laws hold. In the only thing that we have to remember here and kind of take away from this equation is that when we go to take the x partial derivative, we treat y, the other variable, as a constant because it doesn't change at all when you're only taking the x partial derivative. Same thing for, say, the y partial derivative. You can take when you're taking the y partial derivative, you treat x as a constant because x isn't changing if you're only evaluating the rate of change of a function in the y direction. So this is going to be a key point when we go through and do some examples for calculation of the partial derivative. So it's also important to write down that we have some notational, like some other separate notations for the partial derivative. And these vary across sources, but there are a couple common ones that are important to denote. So The first one is the fractional notation, a df dx or df dy. And I'll probably put df dy over df dx. And I'll just put an equal sign between these multiple different notations. So df dx at a given point r naught, or df dy at a given point r naught, this is the same thing as we can use what's called subscript notation. So you could say fx at the point x naught y naught, or fx at the point r naught. Same thing for the y partial derivative. This is sometimes called subscript notation for the partial derivative. Another common notation would be if, say, you have that the output w is equal to f of xy. You could also use this and say that this is the same thing as dw dx at the point r naught, or dw dy at the point r naught. But these are the two very common notations that we'll see and we'll use a lot when we're talking about partial derivatives of a function. The subscript notation and the fractional notation. It's also worth pointing out that in terms of computation, right, and I mentioned this before, but I want to kind of emphasize this again, just so that everyone listening is clear. In terms of computing this partial derivative, so the x partial derivative and the y partial derivative, all of our computational rules from single variable calculus apply almost directly to computing partial derivatives. So you want to kind of brush up on all of your single variable calculus derivative rules, the product rule, the chain rule, the quotient rule, because really this right here is the same thing. The x partial derivative is the same thing as the normal single variable derivative, the x derivative of f as a function of x and fixed at y naught. This is evaluated at x naught. And the y partial derivative is the same thing as the normal single variable derivative of the trace f of x naught y at the point y naught. So this is like saying if you consider to get the x partial derivative, you can consider the trace of the function at y naught, and this is going to taking the normal single variable derivative of the trace at y naught will give you the partial derivative. And same thing for the y partial derivative, that the y partial derivative at any point will be the normal single variable derivative of the trace of the function f along the point x naught. And we'll see what this corresponds to graphically a little bit later on in the lecture for one of our examples. But what I want to do is try to visualize this for functions of two variables. Now again, it's harder to visualize for a function of 3 variables or 4 variables, so we're going to stick with the function of 2 variables, because we can visualize the graph of a function of 2 variables very nicely in 3 dimensions. So for our visualization, what we're going to do is we're going to kind of draw our 3 axes, the x-axis, the y-axis, and the z-axis. and get an idea about what the calculation of the partial derivative is saying at any given point. So what we'll do is we'll consider the following points. Let's say for argument's sake, the function is takes on maybe this value here, this z value here, this z value here, and then this z value here. And the surface looks like this on the boundaries. So this is our surface, z equals f of xy. Maybe it comes up like this and then goes down. And same thing here. Suppose it comes up like this. Kind of goes down to that. These are, say, two traces of the function. A trace at the point x naught right here. So we'll say at this point right here. And this curve right here corresponds to a trace of the function at some value y naught in the domain. So that's this trace right here. So they intersect right here at this point right here. So this value, the z value of the function at this point, this is our point r naught, this is x naught, y naught, and it maps up to this point, this z value, where this z value is given by z naught and is equal to the value of the function at x naught, y naught. So like we showed before, and I was talking about before, that the trace of this function, the derivatives of the traces of this function at a given point is the same thing as the x partial derivative and the y partial derivative. So at this point, the x partial derivative is the slope of the tangent line to this, the trace at y naught, which is the slope of this line right here. And the y partial derivative is the slope of the trace of this tangent line right here to the function. So you see a nice kind of clear picture about what these partial derivatives are representing if you graph them out in 3D. And what we're going to see is that the correct way of defining differentiability of a multivariable function is having, in some sense, the existence of this tangent plane. So you see here that both of these tangent lines form a tangent plane, it's called, or a plane that is tangent to the graph of this function. You can visualize this really at any point on this surface, on a function who has a kind of smooth surface. You can visualize this tangent plane to the function. And you see that if you kind of move around to different points, the tangent plane is going to be it's going to have a different slope in different directions, in the x direction and the y direction. But the idea is that this tangent plane for a multivariable function of two variables is the same concept as the tangent line. So existence of a nice tangent plane is going to lead to differentiability for a function for us. For functions of more than three variables, this concept is the same, only it's harder to visualize. We can't visualize a tangent plane in 4 dimensions, say, for a function of 3 variables. But the idea is that we can still define differentiability via this tangent plane, via what's called the linearization of the function. So in some sense, this tangent plane is a linearization of this function around the point. So around this point. If you get very, very close to the point, in regions very, very close to the point for differentiable functions, the linearization should be a close approximation to the actual function. And this is the idea, the really big idea behind defining differentiability of a multivariable function. But the main idea here is that the main takeaway from this is going to be that partial derivatives are used to define what's called the tangent plane and more generally what's called the linearization. Also known as the linear approximation to a multivariable function. At some point. So these are ideas that we will get into a little bit later on, but really we want to kind of think of these partial derivatives as being the rate of change in each individual direction. The rate of change of the function that we're talking about. So let's go through some examples, and we'll go through 3 examples of how to compute these partial derivatives. And again, I'm only going to focus on functions of 2 variables, but all of these things apply to functions of any number of variables, and including the limit definitions that you saw earlier. So let's consider the function (5x² plus 4xy plus y². The x partial derivative of this function f at any point is going to be computed by taking the x derivative of this expression and keeping y constant. This is going to be 10x plus 4y plus 0 and we computed that using the power rule here, and again the power rule, the derivative of the function x is 1, and you have to treat 4y as a constant because you're taking the x partial derivative here. And then lastly, if you're treating y as a constant, the x partial derivative of y² is just going to be equal to 0. Likewise, df dy is going to be 0 plus 4x plus 2y, which is just 4x plus 2y. And again, this is computed using the fact that x is constant with respect to y. So the y partial derivative of 5x² is 0. The y partial derivative of 4xy, or the derivative of y, is 1. And we're treating x as a constant, So the derivative of y is just 1, which leaves us with 4x. And then the derivative of y squared is 2y. So these are the partial derivatives for this function. We'll consider a slightly more complicated example. Let's do the function g of xy is equal to e to the negative x squared plus y squared. So-called bump function, if you look at the graph of this in 3D, by doing the traces of the function, you'll see that this function looks like kind of a bump at the origin. We've seen this before. There's circular level curves, and it's exponential as a function of x and y. So I'll use the other notation here just to kind of show that you can use either notation. Gx is a function of x and y is going to be equal to the x partial derivative of this function, which we're going to have to use the chain rule here. So the x partial derivative of the chain rule, where we're keeping y constant, is going to be e to the negative x squared plus y squared multiplied by the x partial derivative of this function right here, which is going to be negative 2x. So this is just applying the chain rule from single variable calculus, that the derivative of a function composition is the derivative of the outer function, which is this, times the derivative of the inner function, which is negative 2x. So our result is that gx, the x partial derivative of the function g, is the function negative 2x times e to the negative x squared plus y squared. And here's where I want to mention that there's a little trick that you can sometimes do for calculating the y partial derivative. And this has to do with the symmetry of the function. So if your function is symmetric, which not all functions are, but this function is symmetric with respect to x and y, which means if I replace g of xy with g of yx, so at any given point I swap where x and y are. This is the function e to the negative y squared plus x squared. And not all functions are always equal to the original function when you swap x with y, but you see that this function is. So if you switch x with y in this function, the function is completely symmetric. And what that means is that when you go through and calculate the y partial derivative of this function, the y partial derivative is going to be the same as the x partial derivative, but with x and y swapped. This is going to be equal to negative 2y e to the negative x squared plus y squared. And you'll see that I didn't even have to go through and do any calculations for this y partial derivative. I can just use the fact that this is a symmetric function of x and y and use my previous calculations for the x partial derivative. Now this may not seem like a huge deal for this example, but we'll see in the next example that this is a very, very big idea. It allows us to get very, very fast, quick derivative calculations if we have a symmetric function. I recommend going through and actually using your derivative laws to get the y partial derivative as well, because it's good practice. But I'm going to leave this example here. So we'll call the previous example was example 1. Just number these in bookkeeping. We'll call this example example 2. And we'll consider a third example now. So for the third example, we'll look at the function h of xy is equal to x times y times e to the negative x squared plus y squared. So it's slightly similar to our other computation, or to our other function, a little bit more complicated. dh dx, the x partial derivative. When we look at this, we see here that you have a function of x and y, and specifically, right, we're treating y as constant when we take the x partial derivative. So this is going to be equal to the same thing as the function y times x times e to the negative x squared plus y squared. And so what you see here, we're going to have to apply both the product rule and the chain rule to get the x partial derivative of this function. The first one we're going to have to apply is the product rule. It's going to be derivative, x partial derivative is going to be y times the derivative of x, which is 1, times e to the negative x squared plus y squared, plus x times the derivative of e to the negative x squared plus y squared, which we calculated before from the chain rule is negative 2x e to the negative x squared plus y squared. So this was first we did the product rule here, and then we had to do the chain rule. We can simplify this a good deal by factoring out e to the negative x squared plus y squared to get that dh dx is equal to y times 1 minus 2 x squared times e to the negative x squared plus y squared. And this will be our final result for this partial derivative. And here's where you can hopefully see that our symmetry rule from before comes in very, very handy, because this function is symmetric with respect to y and x. If you plug in x where y is and y where x is in this function, you get the same function. So h of xy is equal to h of yx. And what's nice about this then is that if you don't want to compute the y partial derivative, you don't have to. You can rely on symmetry. So by symmetry, dh dy is going to be equal to x times 1 minus 2y squared times e to the negative x squared plus y squared. Because the function h is a symmetric function of x and y. Now it's important for me to emphasize here again that this is not always true. Example 1 is an example of a function that's not symmetric as a function of x and y. But this function is symmetric, and therefore we can use this trick. So in a second, I'll open up a visualization so we can kind of see that this is giving us, a very, it's giving us exactly that tangent plane and those two tangent lines that we were talking about before. But let's just go through and we'll use these two formulas to give us, a computation. So specifically, we'll evaluate these partial derivatives at the point r0, x0, y0, where x0 is equal to -1, say, and y0 is equal to -3/2. So we're going to evaluate the partial derivative at this point. So using the above equations, we have that hx at the point -1, -3/2 is going to be equal to y, which is -3/2, times 1 minus 2 times x squared, x is -1, times e to the -1 squared plus -3/2 squared, which is the same thing as -3/2 times 1 minus 2, which is -1, times e to the -1 plus 9/4, which finally simplifies to just 3/2 times e to the -13/4. So the x partial derivative of h at the point -1, -3/2 is directly given by this value. This is exactly the slope of the x trace at y equals -3/2. Furthermore, if you go through and get hy at this point, you'll see that hy, or the y partial derivative of the function, the trace for x equals -1/2 is equal to 7/2 e to the -13/4. And you get this by doing what we did before, which is plugging in for x and for y -1 and -3/2 into the equation that we obtained before for dh dy. So what I'm going to do right now is run my Python code to show us a plot of this function, and I'll also show the level curves in the density plot of this function, so we can kind of see all three pictures sort of describing what this function is doing. So here we see a plot of the graph of this function. On the right, I've included the density plot and the level curve plot, along with right here you can see the point -1, -3, or x equals -1, y equals -3/2. So it's this point right here. And I've also included a visualization of the graph of this function on the left with the level curves and density plot underneath it. So you can see what the graph of this function looks like, as well as the tangent plane right here. You see very clearly that the slope of this tangent plane is positive and positive. And the x slope and y slope correspond to the exact values that we calculated previously. It's also important to note here that the x slope of the tangent plane is directly the x slope of the trace of this function at this point, which I've included on the plot. And the y partial derivative of this function, or the y slope of this plane, is the y slope of the y trace at this same point, which I've included right here. So this is pretty neat.